Dear children, the last class we discussed about dimensions of physical quantities. Now, some of the dimensions of some physical quantities already discussed, and some of them as given as homework, and you might have done. No? So, some more physical quantities dimensions we will discuss. Before discussing that one question was given to find the dimension of kinetic energy. So, when it is asked to find the dimension of kinetic energy, first you should know that you know the formula. Kinetic energy is equal to half mv square. No? So here, no need of considering this half. Why? Because half is one numerical value. No, it has no dimension. So no need to consider about this half. So what you will get? You can write it as m. Dimension of m is mass. The dimension of velocity is L t raised to minus 1. No? So L t raised to minus 1. The whole square, so that you will get it as m L square t raised to minus 2. So that is the dimension. So here no need of considering this half. Why not need to consider? Because it has no dimension. Whichever having dimension only to be considered. No, this is one numerical value, so no need of considering that. Okay, clear? No. And now here we will discuss again some of the dimensions, and after that we will discuss the uses of dimension analysis. So, our gravitational constant is there, G, universal gravitation constant. Find the dimension of universal gravitation constant. Okay, dimension of universal gravitation constant. So how to find the dimension? So you should know the relation. In 9th already has studied F is equal to G m1 m2 divided by r square. Where F is force, G is gravitation constant, m1 and m2 are masses, and r is the distance between the objects. So from this we can write G is equal to F r square divided by m1 m2. Okay. Now it is very easy to find the dimension. No. So dimension of G is equal to dimension of F r square divided by m1. Now what's the dimension of F? F is force. Its dimension is m and t raised to minus 2. Again r square is length square divided by m into m square. Or you can write it as, this will become L into L square will become L cube. So m L cube t raised to minus 2 divided by m square. So if it goes to numerator, what happens? M raised to 1 by m raised to 2 is equal to m raised to 1 minus 2. You will get it as m raised to minus 1. M by m square is equal to m raised to 1 minus 2, which is equal to m raised to minus 1. So you will get it as m raised to minus 1 L cube t raised to minus 2. That is the dimension of universal gravitation constant. Okay, clear? So like this you can find the dimension. And next one we will discuss dimension of acceleration due to gravity. G is acceleration due to gravity. Okay. So what is the formula to find the acceleration due to gravity? You can write F is equal to mg. Now force or weight is equal to mg. Now from this you can find G is equal to F by m. So dimension of G is equal to dimension of F is m L t raised to minus 2 divided by dimension of m, so that we will get it as m will get cancelled, we will get L t raised to minus 2, which means acceleration due to gravity also has the dimension of acceleration itself, because it is also acceleration only, so it has the dimension as that of acceleration. Okay, clear? Okay. And you have studied in chemistry the ideal gas equation. ideal gas equation is given by PV is equal to nRT. PV is equal to nRT, where P is pressure, V is volume, R is universal gas constant. R is universal gas constant. T is temperature. Okay. T temperature. P pressure. V volume. And N is moles, no, number of moles. N is the number of moles. So from this you have to find the dimension of R. So how to find the dimension of R? The dimension of R is equal to, you can write dimension of PV divided by dimension of PV. And what's the dimension of P? P is equal to force by area, no? Pressure is equal to force divided by area. So you can write M L T raised to minus 2 divided by L square. So you will get it as M L raised to minus 1 T raised to minus 2. And what's the dimension of V? V is volume. So dimension of V is given by volume. So you can substitute here. So dimension of R is equal to dimension of P is M L raised to minus 1 T raised to minus 2 into L square divided by N. But N has the dimension? It has the dimension of mole, no? Mole into Kelvin. Okay, so you will get the dimension of R as M L raised to 1, or L you can write it as L T raised to minus 2 mole raised to minus 1 Kelvin raised to minus 1. Okay, so this is the dimension of universal gas constant. Okay, is it clear? And now we will discuss to find the dimension of Planck's constant. Dimension of Planck's constant. This Planck's constant is represented by the letter H. We have to find the dimension of H. So to find the dimension of H, you should know the relation, no? So there is a relation between Planck's constant, energy and frequency, that is given by E is equal to H nu, where E is the energy, H is Planck's constant and nu is the frequency of the electromagnetic radiation. This is an expression to get the energy associated with an electromagnetic radiation. Okay, so if nu is the frequency of the radiation, energy associated with that electromagnetic radiation is given by E is equal to H nu. Okay, this relation you will study in this year in chemistry and again next year in physics. Okay, no need to worry about this relation, but from this relation we have to find the expression for Planck's constant. So how to find the expression? So you can write H is equal to dimension of E divided by dimension of E. Okay, so what's the dimension of E? E is equal to M L square T raised to minus 2. And what's the dimension of nu? Nu is equal to frequency, no. Nu is equal to frequency is equal to 1 by T. So dimension of nu can be written as T raised to minus 1. Okay, so you will get the dimension of H as M L square T raised to minus 1. Okay, dimension of Planck's constant is given by ml square t raised to minus 1. Okay. Similarly, another one is that dimension of coefficient of viscosity. Dimension of coefficient of viscosity, and that is represented by one letter. It is beta. This is one Greek alphabet. Beta, which is used to represent the coefficient of viscosity, is given by beta. Okay. So you have to find the dimension of beta. Again, you should know the relation. The viscous force. Viscous force means the opposing force acting when an object is moving through a fluid. Friction is there. No, similar to friction, the opposing force acting when an object is moving through a fluid, that opposing force is known as viscous force. So the viscous force, there is a relation, is given by 6 pi eta Rv. The same expression we will discuss in the second part of this year only. So F is equal to 6 pi eta Rv. From this you have to find the dimension of eta, where F is force, R is the radius and V is the velocity. Okay. F is force, R is the radius of the spherical object, and V is the velocity with which, the constant velocity with which it is going through that. It is falling down through the liquid. Okay. So from this we have to find dimension of eta. The dimension of eta is equal to, you can write F by 6 pi Rv. So here no need to consider about 6 pi because it is numerical value, no need of having dimension. So you can find dimension of F is ml t raised to minus 2 divided by L into L t raised to minus. Okay. Or we will get it as n L raised to minus 1 t raised to minus 1. How? 1 L will get cancelled, here 1 t raised to minus 1 will get cancelled, and this 1 by L, if it goes to numerator, it will become L raised to minus 1. Okay. So m L raised to minus 1 t raised to minus 1 is the dimension of coefficient of viscosity. Okay. Similarly, so many constants are there, so you can find the dimensions of those things. Okay. And now we will discuss about the classification of physical quantities. Okay. So we can classify them into constants and variables. Already you have here constants. Variables. Constants means the value will remain same. There is no change in value. That type of quantities are known as constants. And these constants again we can classify into two. One is dimensional constants. Dimensional constants and dimensionless constant. Dimensional constants and dimensionless constants. Dimensional constant means its value will be constant, but that quantity will have dimension. For example, universal gravitation constant, universal gas constant, Planck's constant, acceleration due to gravity, all those we can say that having constant value but it has dimension. Okay, clear? These are the examples of dimensional constant. Value will be constant but it will have dimension. And dimensionless constant means value will be constant and it has no dimension. For example, pi has no dimension. Okay, clear? Then variables. We can classify again variables also like this only, but it is dimensional variables and dimensionless variables. dimensional variables and dimensionless variables. So what is meant by variable means its value will be changing. No? Dimensional variables means value will be changing and it has a dimension. For example, force, mass, all those. No? Force, mass, speed, velocity, pressure, time, temperature. So like that, so many quantities we can give. Its value will be changing depending on the situation. Its value will be changing and it has a dimension. Next one we will discuss about dimensionless variables. Its value will be changing but it will not have dimension. For example, angle, strain, relative density, its value will be changing. For different materials, its value will be changing. No. Angle will be changing, strain will be changing, relative density will be changing. No. For different, you can have for 30 degree, for different angles, value will be changing, but it has no dimension. Why? Because angle in previous class we discussed angle is equal to arc by radius. Similarly, we discussed about strain. Strain is equal to changing dimension by original dimension. Linear strain, volume strain, that we discussed in previous class. No, it has also no dimension, but its value will be changing. Similarly, relative density. What is meant by relative density? Relative density is equal to density of material divided by density of water. So both dimension will get cancelled. So again we can say that is another example of dimensionless variables. Okay, is it clear? So you understood clearly, difference between constants and variables. Okay, now we will discuss the applications of dimensional analysis. Why we are studying this? Is there any use of this? So this dimensional analysis have three uses. The first use today we will discuss here, to check the correctness of an equation. So uses of dimensional analysis. The first use is that to check the correctness of an equation. We can use this dimensional method that whether a physical relation or physical equation is dimensionally correct or not. Okay. So this it is also known as principle of homogeneity of equation. Principle of homogeneity of equation. So what is meant by this principle of homogeneity of equation? That is, a physical equation will be dimensionally correct if and only if each term of the equation on the left hand side and right hand side are equal. Okay. A physical relation or equation is dimensionally correct if and only if each term of the equation on LHS and RHS are equal. LHS and RHS are, this is what is meant by principle of homogeneity. Tell you in detail. It's very simple. Only same dimensional quantities can be added or subtracted. That is what is meant by this sentence. Principle but homogeneity of equation. Same dimension of quantities can be added or subtracted. We can add one force with another force. We can add velocity with velocity. Is it possible to add velocity with mass? Is it possible to add time with temperature? Is it possible to add current with mass? So only current with the current can be added. No. So only same dimensional quantities can be added or subtracted, and that is what is meant by this principle of homogeneity of equations. For example, we can see the simplest equation that already you have studied in 9th standard. V is equal to U plus LT. So we can see already you know that this equation is correct. So we can check that whether this equation is dimensionally correct or not. So we can see, we can start from the LHS part. So LHS part is the dimension. V, velocity is the final velocity. So dimension is given by LT. Okay. Now we can see in RHS part each term means here U is one term, another term is LT. No? So each term should have the same dimension. So here U is having the dimension LT raised to minus 1 itself. Again we can see the dimension of AT. Acceleration has a dimension LT raised to minus 2 into L, so that we will get it as LT raised to minus 1. Which means each term here, if you are writing V is equal to U plus LT, so you can write dimension here LT raised to minus 1 is the dimension, here dimension is LT raised to minus 1, and here again dimension is LT raised to minus 1. Which means each term in this equation has the same dimension. Okay, each term. Not necessarily that you have that you don't add. This is but LT raised to minus 1 plus LT raised to minus 1 is equal to 2 into LT raised to minus 1, like that, no need to write. Because here we are checking the dimensional consistency. Okay, whether the equation is dimensionally correct or not. So each term should have the same dimension. Okay, then we can say that equation is dimensionally correct. Is it clear? Okay, so we will discuss another example. Check the dimensional consistency of the equation. T is equal to 2 pi into root of L by G. T is equal to 2 pi into root of L by G. When T is time period, L is length and G is acceleration due to gravity. So we will start with LHS. So LHS has a dimension T LT. Now we will go to the RHS. So here no need to worry about 2 pi, it is constant value. No need to worry, only we have to consider dimensional quantities. So you can write it as dimension of root of L divided by G has the dimension LT raised to or you can write it as L will get cancelled. 1 by T raised to minus 2 will go to numerator. So it will become T square or you will write it as T square under root you will get plus T. So you can say that dimension of LHS and dimension of RHS both are equal. So we can say that this equation is dimensionally correct. Okay, is it clear? Now another example we can see. F into S. F is force, S is displacement, M is mass, G is final velocity and U is initial velocity. You have to check whether the equation is dimensionally correct or not. So you can start with the LHS part. So LHS, we can see dimension of F into S, which is equal to M L T raised to minus 2 into L, which is equal to M L square T raised to minus 2. Okay. Now we will come to the RHS part. So RHS, each term we have to see. First term is half M V square. So here no need to consider about half. Why? Because it is a numerical value. It has no dimension. So no need to worry. So M into V velocity has dimension T raised to minus 1. Its square will be there. So you will get it as M L square T raised to minus 1. next term half m u square. So again you will get same because it is find initial velocity. So it is to minus 1 whole square. So you will get again plus m l square t raised to b. So you can write like this: m l square t raised to minus 2. Here dimension is this. Here m l square t raised to minus 2. And this term also has a dimension m l square t raised to b. So no need to write that this minus this is equal to 0. I told you this is only to check the dimension. We are not adding or subtracting, only to check that whether each term has a dimension. Okay. So we can say that this term, each term in this equation has the same dimension. So this equation is dimensionally correct. Okay. Is it clear? So this is the significance of this dimensional analysis. We can check whether an equation is dimensionally correct or not. And one thing is that if it is dimensionally correct equation, not necessary that that equation will exist. But if it is a dimensionally wrong equation, there is no chance of its existence. If an equation is dimensionally wrong, it will not exist at all. But if an equation is dimensionally correct, it may or may not exist. Why? For example, if we are considering that equation b is equal to u plus l. This is the actual equation. No? So if instead of b, if we are writing b is equal to 2u plus half u. This is also according to dimensional analysis, it is correct. If you find here each term, you will get the same dimension. No? Or you will get, here you will get it as l t raised to minus 1. Here again u has no value, we no need to worry. Again here you will get it as l t raised to 1. So here each term you are getting the same dimension. But this is not actual equation. That's why I told you dimensionally correct equation, there is a chance of their existence, but if a dimensionally wrong equation is there is no chance of its existence. Okay? Is it clear? So one or two questions we will discuss and wind up the session. One question is that force is given by F is equal to A root x plus B t square. Find the dimensions of A and B. Find the dimensions of A and B, where F is force. What is F? F is force, x is displacement, and T is time. We have to find the dimension of A and B. So how to find the dimension? Very simple. Only same dimensional quantities can be added or subtracted. So you can write dimension of F should be equal to dimension of A. Can you write? Can you write? Why? Because same dimensional quantities can be added or subtracted. So each term should have the same dimension. Or we can write dimension of A is equal to dimension of F divided by dimension of root x. And what's the dimension of F? F has the dimension ml t raised to minus 2 and divided by it will be l raised to half. No, root x can be written as l raised to half. Okay. Now what you will get? You will get it as m l raised to half t raised to l raised to 1 by l raised to half is equal to l raised to half. Okay. Is it clear? Similarly, you can find the dimension of B. How? Same way you can write dimension of F is equal to dimension of B is, or B is equal to dimension of F divided by B square. So, what's the dimension of F? ML t raised to minus 2 divided by T square. So, you will get it as dimension of B is equal to m l k raised to minus 4. Okay, m l k raised to minus 4. Is it clear? So one more example we will discuss. P is equal to f minus a by bt. P is equal to f minus a by bt, where P is pressure, F is force, T is time. Find the dimension of A. You have to find the dimension of A. So first of all, you should find the dimension of A and B. No. So here it is very simple. Same dimensional quantities can be added or subtracted. So from this part, numerator part, very easily we can write dimension of F is equal to dimension of A. No. Dimension of F is equal to dimension of A according to the principle of homogeneity of equation. So dimension of A is given by m l t raised to A. Okay, clear? Now you have to find the dimension of B. So you can write this equation. Dimension of F is equal to dimension of F minus A divided by dimension of B. So F and A both are having same dimension, which is given by 0. This is dimension of P. Dimension of P is equal to dimension of F minus A by dimension of Bt, and here both are having same dimension, so you can write it as m l k raised to minus 3 divided by dimension of B into dimension of B. So from this you can find the dimension of B. How? Dimension of B is equal to m l k raised to minus 2 divided by the dimension of pressure. Pressure equal to force by area. So you will get it as m l raised to minus 1 t raised to minus 2 into t2. Okay. So t raised to minus 2 will get cancelled. What will you get? M will get cancelled. You will get it as L square t raised to L square t raised to minus 1. That is the dimension of B. How this L raised to minus 1 will go to numerator? So L raised to 1 into L raised to plus 1. So you will get L square 1 by t, it will become t raised to minus 1. So you got the dimension of B and dimension of A. Now can you find the dimension of A into B? So dimension of A into B is equal to dimension of A. What is the dimension of A? Dimension of A is given by m l k raised to minus 2 into dimension of B is L square k raised to minus 1. So what we will get? M L cube t raised to the dimension of A. Okay, is it clear? So these things only you have to keep it in mind. Same dimensional quantities can be added or subtracted. Otherwise, it will become too much complicated if you write it separately. F by bt or A by bt like that. If you write, it will become much more complicated. So in this way, you can find the dimension of A and B. And one more thing you have to keep it in mind that already I told you, if a dimensionally correct equation, it's not necessary that actually it will be existing. Not necessary, but if it is a dimensionally wrong equation, there is no chance of its existence. Okay, if it is dimensionally wrong, it will not exist. So today we discussed one of the uses of dimensional analysis. Other two uses we will discuss in the next class. Okay.